Hello, this is the second video on calculus, and in this video we're going to be covering methods of taking derivatives. So this is about differential calculus, and as I mentioned in the previous video, we don't want to use the limit definition of the derivative directly that we covered in the last video. Rather, there's a series of rules that we can use and combine together in order to take derivatives of actually quite complicated functions. And there's essentially three rules, which are called the product, quotient, and chain rule that we're going to go over. I did want to mention one thing I forgot to mention in the previous one. In the next video, actually, we're going to be talking about a concept that I think will be new to everybody called partial differentiation. So I didn't mention that. There is some new material there. But in this video, we're talking about methods of taking derivatives. Okay, so as there's these three rules, product, quotient, and chain. As I think these are review for most people, I'm going to focus mostly on doing examples and showing you really how the rules work, how we can apply them in particular cases. And so we'll look first at the first two of the rules, which are sort of two sides of one coin, the product rule and the quotient rule. And so these are applied when we have either the product or quotient of two functions, and we want to take the derivative of that product or quotient. So we have, for example, in the product rule, a function u times a function v, and we want to take the derivative of the function u times v in terms of the derivatives of u and v. And similarly, for the quotient rule, we have u divided by v, and we want to know the derivative of u divided by v in terms of the derivatives of u and v. And so these are the two rules. The product rule gives us uv prime is equal to u prime times v plus u times v prime. And I won't bother to say the quotient rule in words, but you can see it here. And one important thing to realize is that these can be proven based on the limit definition of the derivative, so the limit of the slopes of secant lines as we went over last time. And if you want a challenge, I would suggest that you try to prove these. It's a bit tricky, but it's possible, so you should be able to do that if you want to understand at a deeper level. But for the class, the purpose of the class, it's enough to understand how to apply these to particular examples, and we're going to go over a few examples now. And so first I'll look at the product rule. So here we have the product rule at the top of the slide for reference, and here we have a product of two functions, x squared times sine of x, and we're going to want to take the derivative of that using the product rule. Okay, so we have x equals x squared times sine of x. And so the two functions which are forming the product here are x squared, which we'll call u, and sine x, which we'll call v. U is x squared, v is sine of x. And so these are functions that you have to know the derivatives of, and these were ones on the table that I presented last time. The derivative of x squared, this is one of, well, that's the one we went over, 2x. The derivative of sine, one of the examples from the table from last time, is cosine. And so then we can apply the product rule in order to write down the derivative of this function f, which is the product of u times v. So the derivative of this function f, derivative of the product, and the product rule says that this is u prime times v plus u times v prime. And we have worked everything out here. We can just put it into the formula. Okay, so I made a mistake which has been edited out, but I skipped that. I wrote down u instead of u prime. But yeah, so we have, putting these into the product rule, we have u prime is 2x here times v, which is sine x, and u x squared times v prime cosine x. Okay, and so this is the derivative of f using the product rule. I am going to do another really very similar example. Say now f of x is e to the x times cosine x. Once again, this is a product of two functions. E to the x times cosine of x. And, well, the function u in this case will be e to the x. The function v will be cosine of x. And we know the derivatives of those from the table that you have to memorize. Derivative of e to the x is e to the x again. Easy one to remember. And v is cosine of x. Derivative of cosine of x is negative sine of x. Okay, and so then we have everything we need to apply the product rule. The derivative of this function f equal to the derivative of u times v. And so the product rule says this is u prime times v plus u times v prime. U prime is the same as u in this case, so e to the x, v is cosine x. And then we have u, e to the x, v prime is negative sine of x. And so we can simplify this slightly. We factor out the e to the x, you have e to the x cosine of x minus sine of x, the derivative of this product, using the product rule. Okay, so this is the product rule. I'm not going to do any more examples only showing the product rule. We'll move on to the quotient rule. And so once again, I should have it here at the top of the slide for your reference. And here we have a quotient of two functions, sine of x divided by e to the x. I'll apply the quotient rule in order to take the derivative of this. And the two functions we're dividing, sine of x and e to the x, these are ones that are in the table, so you can know what the derivatives of those are straight away. Okay, so we have h of x sine of x over e to the x. Okay, so this is u divided by v, where u sine of x, v, x there, the v is e to the x. So the derivative of u sine of x is cosine of x. Already done these in the previous example, but once again, they're just ones you look up in the table. And then we apply the quotient rule. The quotient rule says the derivative of this quotient of u divided by v is derivative of u times v minus u times the derivative of v prime divided by v squared. Have everything, all these derivatives, and so we just put them into the formula. So u prime is cosine x, v is e to the x, minus u is sine x, v prime is e to the x, divide by e to the x squared, which is e to the 2x. Okay, and here we can factor out the e to the x in the numerator and cancel with one of the factors in the denominator, and simplify this to cosine of x minus sine of x divided by e to the x, the derivative of this function h using the quotient rule. All right, so I'll do one more example using the quotient rule. And so the next example will be f of x equals the tangent of x. And so this isn't immediately written as a quotient, and so this one requires a little bit more thinking than the previous one. We don't just see what the functions are. But if you're familiar with trigonometry, as you should be, then you should know that the tangent of x is sine of x divided by cosine of x. And so it's a quotient of sine and cosine. So you can apply the quotient rule in order to take that derivative. this case, we have f of x, tangent of x. As I said, from trigonometry, the tangent of x is defined to be the sine of x divided by the cosine of x. So it is a quotient of sine and cosine. So we can take u, sine of x, b to be cosine of x. The derivative of u, derivative of sine is cosine. The derivative of v, cosine is negative sine. And so in the previous few examples, I've been writing out the quotient rule fully in order to stress how it works. But when you do these, as you do a lot of it practice, you get used to it, and you don't have to write out the quotient rule every time. You can remember how it works. And so this time, I'm not going to write it out. The derivative is f is this quotient of sine of x and cosine of x. That's going to be u prime cosine of x times v, which is also cosine of x, minus v prime, which is minus sine of x, times u, which is sine of x, divided by v squared, cosine squared. And so we have, well, we can cancel these two negative signs. -1 times -1 becomes +1, and combine the cosines here together. Cosine squared x plus sine squared x divided by cosine squared of x. And now, I hope you see how this can be simplified. So this is something that comes from trigonometry. If you don't see how it can be simplified, you may need to review trigonometry. Cosine squared plus sine squared is always 1. This is by the Pythagorean theorem. Pythagorean identity in trigonometry. So the numerator here is 1, and this derivative is just 1 over cosine squared of x. And we define a trigonometric function secant, which is 1 over cosine, so you can write this also as secant squared of x. So the derivative of tangent is secant squared x, or 1 over cosine squared x equivalently. Okay, so this is the quotient rule. I looked at a few examples. There's one more rule that I haven't covered yet, which is oftentimes the one that people struggle with the most if they've not seen it before. And this is the chain rule. It's the rule that allows us to take a derivative of a composition of functions. So if the function is a function f of u, and then u is in turn a function of x, it's called a composition of the two functions, u of x and f of u. And the formula for the chain rule, when we want to take a derivative of a composition of functions, is really best expressed using the Leibniz notation. So in the previous two cases, we used the Newton notation for the derivative with the prime, and the chain rule is really best expressed with the Leibniz notation, the dy dx. And the reason is that you can formally think of the du's here as canceling out. So you want to calculate dy dx, and y is a function of u, which is its turn a function of x. You take the derivative of y with respect to u, then you take the derivative of u with respect to x, and you multiply them together. That's the chain rule. Okay, and so let's look at an example using the chain rule, just as with the product and quotient rules. So here we have y equals sine squared of x. So this is a composition of two functions. First, the sine function, and then squared function. So sine of x squared. And so in order to write it in the form, so we can apply the chain rule, we take u, the sine of x, and when you do that, then y is u squared. Y is the sine of x squared. And so then you can apply the chain rule. So we have dy x, the derivative of y with respect to u, times derivative of u with respect to x. So you have to take the derivative of y with respect to u, the derivative of u with respect to x. So derivative of y with respect to u, use the formula we actually derived last time straight from the definition with the secant lines, is 2u, that part, and then du dx, the derivative of sine is cosine. We've gone over that times. All right, and so then you can substitute back in what u is. So u is sine of x, and so you have 2 sine of x cosine of x. And there is a trig identity, which you may or may not remember. This one is not quite as basic as the Pythagorean identity from last time. It's the double angle identity for sine. So this is also equivalent to sine of 2x. So the derivative of sine squared of x is sine of 2x. All right, so that's one example with the chain rule. I'm going to do one more chain rule example. So we'll differentiate this function, 1 plus x squared, all raised to the 20th power. So you could do this one by multiplying out this 1 plus x squared and using the distributive rule algebra to write this big polynomial. It would be a 40th order polynomial. And you can take the derivative individually in each of the terms individually. But you can also use the chain rule on it. It's quite a bit easier. So now here in this example, y was 1 plus x squared raised to the 20th power. And so we want to write this as a composition of functions. So we're going to take u to be 1 plus x squared. And y is u raised to the 20th power. So it's a composition of these two functions. And then we apply the chain rule. Y x y du times du dx. So dy du is the power rule for taking derivatives. So the derivative of u to the 20th with respect to u is 20 times u to the 19th. Y du, and then du dx. Well, so this actually uses a rule I haven't explicitly talked about in the lectures, which is the fact that the derivative is linear. When you have a sum of terms, you take the derivative of this sum of the three terms. You can take the derivatives of each of the terms individually and then add them up. And so the derivative of u with respect to x, the derivative of 1 is constant. That's a constant, so the derivative is 0. Derivative of x is 1. And then plus the derivative of x squared is 2x. Okay, and so we have the derivative is 20 times 1 plus x times u, which I'll plug back in the formula for u now. 1 plus x squared raised to the 19th power. And the derivative of this function is 20 times 1 plus 2x times 1 plus x squared raised to the 19th power by the chain rule. Okay, so this is the chain rule. And we have also covered this rule for taking the derivative of sums. Hadn't been mentioned before. When you take the derivative of a sum of terms, that's the sum of the derivatives. Okay, I'm going to do one more example. So these can actually get quite complicated because you can combine the rules by taking products and compositions in many different ways. And so this is a last example that I'm going to do is a combination of the methods, or we have to apply a combination of the rules in order to take the derivative. And so we have y equals x squared times sine x. E to the x squared times sine x. And we want to take the derivative of this, dy dx. And well, you first notice it's a product of these two terms, e to the x squared and sine x. So let's say dy x is equal to, by the product rule, the derivative of the first term, so derivative of e to the x squared with respect to x times the second term plus the first term, e to the x squared times the second term, or the derivative of the second term. And well, we know the derivative of sine right away, that's cosine. So this second summand here, we know what it is. It's e to the x squared times cosine of x. But the first one, we need to know the derivative of e to the x squared. And in order to calculate the derivative of e to the x squared, you have to use the chain rule, because this is a composition of the function e to the x and the function x squared. So for this one, we apply the chain rule. And so when you apply the chain rule, the derivative of e to the x squared with respect to x is equal to the derivative of the e to the u, where we let u be x squared with respect to u, times the derivative of u, which was x squared, with respect to x. Okay. So the derivative of e to the u with respect to u is e to the u. Derivative of x squared with respect to x is x. And then u is x squared. So let's plug that back in. E to the x squared times 2x is the derivative of e to the x squared. Okay, and so you can put the derivative of e to the x squared back in the original formula for dy dx. And get the final derivative for the function we wanted to differentiate, e to the x squared times sine x. So we've applied both the product rule and the chain rule. So the derivative of e to the x squared is 2x e to the x squared. And this formula is found for derivative of e to the x squared times sine x plus e to the x squared times cosine x. And if you want, you could simplify this by factoring out the e to the x squared. So not really necessary, but you have e to the x squared times 2x sine x plus cosine x. Okay, so this is a bit more complicated because we have to apply two of the rules, the product and the chain rule. And you could see you could write really quite complicated functions. In fact, any function that you can write as a product, quotient, and composition of the functions where we already know the derivatives can be differentiated by combining the rules in some way. And so, well, that's the end of this video. As always, learning how to do this type of differentiation just requires a lot of practice. And so if you're a bit confused using the chain rule or the product or quotient rule, what you should do is just do some practice. And there are exercises that are available in the exercise sheets. There's also recommended texts that are posted on the website. You can look at those texts for additional examples. You can also look at some of the other links on the Blackboard site, which give you links to more examples if you're still unsure about this. Okay, in the next video we'll move on and we'll talk about partial derivatives, which I believe is a new topic for most people.